Being a photon is nice. You are light, you can travel, you can point to the emitter, but you have a small big problem. You interact. You are not like a neutrino that is very difficult, has difficulties to interact with matter, with material. As a photon, you can be distracted in your travel and absorbed in your travel. This we will see together in the next lecture. This is one of the ways in which we study quantum gravity actually with photons, studying this interaction of the photon in its way to work. Therefore, there is a sort of gamma ray horizon in which, if you go too far, then the probability of detecting a high energy photon from a distant source becomes too small, and you cannot access the far universe with gamma rays. And this is why neutrino astronomy is a very powerful tool to complement gamma ray astronomy, right? You do not really have this process of absorption for neutrinos, so you can access even very distant sources. Then why do we study photons from the cosmic object if we have neutrinos that can go far away? Well, that's because neutrinos are very difficult to detect, and at the moment we have just a bunch of them, especially at very high energies. Okay. Good. So here is just a sketch of the different processes involved in gamma ray emission from an astrophysical source. We have two classes of models. The hadronic models, in which you have in some way protons and pions acting in the production of the photons, and we have leptonic models, in which you have also connection with the synchrotron emission. I will not go into detail because we need to go to see today how do we study, how do we collect these photons. So the first important thing is to create categories, bands, because as we said before, we have a huge part of the electromagnetic spectrum covered by these gamma rays. So we start cutting these bands into pieces, and we define low energy gamma rays below 30 MeV, high energy between 30 MeV to 100 GeV, very high energy, that is the value in which I work, magic, telescope, and so on, 100 GeV, 30 TeV, ultra high energy, 30 TeV, 30 PeV, and extremely high energy above 30 PeV. So we have more than 10 order of magnitude, and as I'm showing you here in this example, this is the emission of one of the most famous gamma ray sources, the Prandtl nebula, that is one of the bright spots in the Fermi sky, is a galactic source. And here you see a nice collection of spectral measurement from the low energy range below 30 MeV. This is in MeV. This is the square of flux. We will see it in a minute. It's a spectral energy distribution. And you see, you start at low energies, you have points from one experiment, then increasing, you change experiment. Because you cannot cover all these huge bands with the same experiment. You need to collect with different experiments, different pieces. And you see that more or less these bands correspond to bands of different experimental techniques. So these are experimentally driven, these definitions. And also, this plot is too small to cover all the energies. There is an addition at extremely high, at ultra high energy, that hopefully up to the extremely high energies, in which you can see the most recent result of the LASO, going up to 100 TeV in this case for the Trav nebula measurement. Okay? So really, we have a lot of different experiments and experimental techniques making the same measurement, but in a different energy range. So now some definition of the main tools that we use to study an astrophysical object. I decided to focus on these three different tools. One is the light curve. I'm sure you are familiar on what is a light curve, but let me just repeat it for further reference. A light curve is a flux of photons above a certain energy. It's extremely important that every time that you see a light curve, especially if you do quantum gravity, you use this light curve, you pay attention on the energy threshold or the energy band in which you are looking at it. So as Maurizio said before, please always look at the axis and what really the plot is telling you. Before even looking at the data, look at the axis and the energy in which you are focusing the attention. And then you can start to see, okay, this is a light curve, so what is it telling us, this plot? This is the flux above a certain energy as a function of time, okay? So we are looking at the flux changes in time. And in this case, you see the scale is minute here. So it means that this source above 50 GeV is emitting a variable flux, and the variability time scale is at the minute scale. Okay, this is already an important information. Then another tool that we use is the differential energy flux, dN over dE. This is how many photons arrive as a function of their energy, the surface of the detector, or the detector, and the time. So it's a rate of photon as a function of the area of the detector. You have seen this plot already. And then we have the spectral energy distribution, that is this plot multiplied by E squared. Why do we use the same plot but multiplied by E squared? That's simple. Let's look again at the Crab nebula. If you plot the Crab flux, not the spectral energy distribution, but the flux, the N over dE, the scale would be giant, okay? By multiplying per E squared, you somehow reduce the scale in y-axis, and you are comparing not the number of photons at a given energy, but the energy density released in a process. So this plot is telling us that the energy here, you see that the level is almost the same, is equal to the energy here, the energy density released. But the number of photons here is much more numerous, is higher than here, because the energy per single photon is less. So to emit the same amount of energy, you need more photons, okay? So when you see these plots, you see two bumps, for example, one at low energies and one at high energies, this is telling you that at low energies, and let's suppose that they are at the same level, at low energies and at high energies, you are emitting the same amount of energy. But the number of photons released are extremely different. If you go at extremely high energies and you have the same level, it means that you have very few photons there. Okay, so very often, gamma rays, especially at the highest energies, is a matter of statistics. Even if the energy release is high, you have very few photons that you can detect, especially if you have a limited area of the surface, because here you are looking at as a function of the area, right, of the detector. So let's look now again on the Crab nebula. Yeah.
But one measures directly the number of photons or the energy. To go from there to the differential.
You multiply by E squared.
No, but the differential, the density of flux. No,
you measure
the N over D.
You measure the N over D, and then you build.
You measure the flux, the number of events.
Yes.
Not the differential flux.
Yeah, well, yes. You measure the number of events, yes, and then you know how much time you spent to this observation, and what is your detector area.
But the number of events is the integral over the energy of the differential flux. So if you know the result of the integral, you don't know the integral.
it depends on what you measure. If you can resolve the energy of the photon, you measure in beam of energies, and you build the differential flux. You always measure pieces of integral flux, but then you fold with your, you got to know your instrument, and you build the differential flux, and then you build the spectral energy distribution by multiplying values. Okay, so let's come back again at the subnebula total emission. This is the spectral energy distribution of the crab from radio up to the high energy range. You see that you have a huge bump in at low energies and a smaller bump at the highest energy. This is not always the case. For example, in blazars, you might have that the second bump is brighter spectral energy distribution than the first bump. So, of course, it's extremely powerful and important to measure in a broad energy range so that you know you have an overview of all the photons, all the processes that are taking place in this accelerator. Yeah, speaking about blazar, I'm showing you now another example. So I show you the spectral energy distribution of a galactic source, the Crab nebula, that is a supernova remnant. This is the spectral energy distribution of the famous neutrino blazar. This is the blazar for which it was for the first time that a blazar was associated with a neutrino emission in 2018. And it's a sort of a mess, you know. You see many points scattered around. Where are the measurements? Well, that's because blazar emission is highly variable. So very often you see plotted together all the data, new data. Usually the convention is that all data are plotted in gray. So they are archival data. You see here, archival. And all colored data are more or less simultaneous. Why more or less? We will see that later. It's extremely difficult for instruments of different bands to observe simultaneously. Not only because they have to agree on when to look at a certain point, but also because certain instruments are not sensitive enough if they do not collect data for enough time. So it's always difficult to build such kind of plots. In particular, this is a multi-messenger plot, not only multi-wavelength. Why? Look at the highest energy. You see they try to plot the neutrino energy also here. Another example of multi-messenger plot is this one. This is extremely famous. It went into all newspaper, right? That was the first detection of simultaneous emission from gravitational wave and gamma rays. These are gamma rays, these are gamma rays at a different energy, and this is the gravitational wave signal. In this case, what the scientists wanted to study was, first of all, the time information. In fact, they are using a light curve plotted. You see, it's the flux or the counts as a function of time in seconds. So the scale is crucial. So this means that this gamma ray instrument and also the gravitational wave antenna are sensitive down to second scale. That is not always the case for instruments. So I'd like now to briefly mention what are the different science cases covered by gamma ray astronomy. As I said before, this is a huge branch of astrophysics, and not only. We basically study non-thermal phenomena, what happens in jets, for example, at all scales, galactic and extragalactic. We study the interaction between particles and matter in supernova remnant, as you have heard before. Transient event, extreme events from the sun, because also the sun emits gamma rays, and the diffuse emission that we saw before in the Fermi map. But with gamma rays, you can also do cosmology. That's important because if you try to do cosmology with gamma rays, you are actually trying to study a process in a completely independent way than traditional methods. So this gives you the possibility to test hypotheses with independent methods. We will see some examples at the next lecture. And then you can do fundamental physics with gamma rays, quantum gravity, testing Lorentz invariance violation, for example, but also axial light particles and dark matter searches, of course, not yet detection, unfortunately. How do you study quantum gravity with gamma rays? I'm concentrating here only on the tools that you use. We will go the details in the next lecture. First of all, you can do studies of quantum gravity looking at the time arrival of photons. To do so, you need light curves, right? Trying to build the light curves as fine as possible because you want to see a difference in the arrival time. So it's crucial that if you want to do this measurement, you have an instrument that is capable of detecting with good resolution the arrival time and the energy of the photon. Another way to do quantum gravity or search for Lorentz invariant variation with gamma rays is the study of spectral energy distribution, and in particular the deviation from the standard scenario expected for photon propagation. Again, focus now only on the message that to do so you need to study spectral energy distribution, okay, and trying to see the shape of the spectrum in order to disentangle between models. We will see this on Sunday. Okay, now we start to focus on really the detection of gamma rays. This was one of the first videos released by the Fermi Lab telescope as it sees the sky. Basically, the search for gamma rays, the detection of gamma rays, means trying to understand where do they come from. First, you need to identify the portion of the sky, the emitter, as much precisely as possible. Then you want to define the energy and the time. All this, if you want to build a good detector, you must do this with the best resolution possible. Also, you have another huge problem of gamma ray astrophysics that is trying to do signal background rejection. Every time you do a measurement in physics, you always have backgrounds, but in gamma ray astronomy, this might be really a demanding task because your background, what will be the background trying to catch gamma rays? We will see it. The background is really dominating. Okay, so the first basic information about the study of gamma rays, you are already aware of that. We cannot detect gamma rays from Earth, right? Because we have a wonderful shell, the atmosphere. The atmosphere is protecting us from cosmic radiation, gamma rays, but also almost all the other bands except optical light and radio waves. So if you want to detect gamma rays, you need to go into space, right? Or to use the atmosphere itself as part of your detector. These are the two main domains of gamma ray observations: direct detection from space or Earth-based detection using the atmosphere as part of your detector. Indeed, in the atmosphere, something will happen when a gamma ray hits the nuclei of the atmosphere. And what happens is might be, if the energy is enough, might be so bright that you can detect it. Now at the observational panorama. The gamma ray band is large, and the observational panorama is complex. You have really different instruments with completely different techniques. You see photon scattering in the low energy band. This is where gamma rays start. Photon scattering, per tracking detector, per sharing probe, and water sharing probe as a first graph approximation. Now I would like to focus on how can we define an instrument. Is an instrument good to do a specific observation or not? To do so, usually we characterize different parts of an instrument, different scientific capabilities. The first one is the sensitivity. This is the spectral energy distribution plot, but looking at what is the minimum detectable signal from every single instrument, okay? So in this plot, what is the best, the most sensitive instrument? Tell me. Is the minimum energy density detectable in a given amount of time, the sensitivity? So which is the best, this one or this one? Think a bit. You want to be the best. You want to observe things. So what is the best here? Forgetting for a moment the energy axis, of course. No. Sorry. This one?
Because it starts with lower energy, as you mentioned.
I want to detect low fluxes. Yes, so of course it's difficult to compare things in different energy ranges, but let's say the most sensitive instrument in the gamma ray band as a matter of minimum sensitivity is this one, because it can detect even very faint sources, okay? Faint means that the flux emitted is low. This is the total energy emitted, the flux emitted. Well, this is less sensitive. So now let's focus, for example, in this case, in the same energy band that is easier, okay? You usually what you see is that all instruments are high there, are the highest. And then with the progress advancing, you have the sensitivity going down because you improve your ability of detect faint fluxes, okay? So usually when you have new generation of detectors, you go down in this scale because you're able to detect even faint flux from a source. We can discuss later if you have not understood. Another difficult thing to take in mind is that we often see this plot drawn on our spectral energy distribution, no? But not all the lines have the same meaning. This is the minimum amount of flux detectable, but you need to consider a specific time for the detection. And in case of satellites, you use 1 year. In case instead of ground-based detector, you use 50-hour observations. So these two, the sensitivity of ground-based and satellite detectors are not really comparable. Why that? That's because of this reason. A satellite is almost always patrolling the sky, okay? So it's always taking data. Its duty cycle is very large. It can observe for 100% time. A ground-based experiment, instead, can observe only very often in limited conditions, like moonless night or only during night accepting some light or all day, depends on the technique. So it's not easy to compare instruments that have a different exposure to the sky. For example, for Cherenkov instruments, in a full year, very often they collect 50 hours from a single source. This is why we use 50 hours. It's the typical detection time for a source at gamma rays. So the duty cycle, the effective observation time for different kind of instruments can range from 1,000 hours that are the Cherenkov experiments looking only in dark time to more than 9,000 hours per year. It's extremely variable. And now let's assume that you want to see events, you want to monitor events, right? Then you need to cover the sky as much as possible. So you need a large instruments with a large duty cycle, because if you can observe only part of the night, you cannot really monitor the sky, the event of the sky. It's better to do so with instruments that can observe always. The problem is that these instruments are only at low energies, because at high energies we cannot observe from space. The fluxes are too low. So observations are always a compromise between what you want and what you can do. Another thing to take into account when you compare instruments is the transient sensitivity. Again, here we have E squared N over V, so the spectral energy distribution plot, but considering the minimum flux detectable by an instrument. This time we are looking as a function. Here we have the energy, but here we have the time. What does it mean, this one? It means that you can look, and we said before, this plot is done with 1 year, 10 years of exposure from the satellite. You see here it's written 10 years in this case. But then if we consider the time evolution of this sensitivity, you will have a complementary view on what is doable with an instrument when you look at a point source. The sensitivity for 1 hour observation, for example, from a satellite is very poor, because it needs to collect data for 1 year to reach the good sensitivity. Instead, the ground-based experiments are more performing as a function of time for short transient. And again, this is another piece of useful information when you want to study transient event and short event, like quantum gravity. If you want to study something that lasts 1 minute, it will be very difficult to do that with Fermi data, unless the event is extremely bright. You can do that with less sensitive experiment, but if you look at the transient part, then you will be more sensitive to this transient. Coming now to something more easy, the energy resolution. The energy resolution is the ability of an instrument of detecting a specific energy. No? It's the minimum width of your error bars index when you do a spectrum. And it's extremely important, for example, when you do spectroscopy, to have a good energy resolution, and this is relevant in the low energy band. And it's, of course, it might be energy dependent. You see the energy resolution, for example, of this is a ground-based experiment, CTA. It is not very good at low energies, but then it improves going up at high energies. And finally, let me mention the angular resolution. We said before, a photon is cool because it tells us where does it come from. But then you have to be able with your detector to reconstruct this direction. And that is the different thing, okay? So the PSF, the point spread function, the angular resolution, tells you this. Tells you the ability of reconstructing on what is the width of a point-like source for a specific detector. It's very important. If you want to do, for example, morphological study, like in this case, you want to see, not only you want to count photons and their energy, but you want to localize them in a narrow region of the sky. Then you need to have a very good angular resolution. And it's pretty difficult to obtain this. Then what happens if let's assume you have two photons from two different regions, but they are below your resolution. Then what happens is that you will not resolve them. You will see them as a single point-like source. The field of view. The field of view of an instrument is its ability, how much sky it can cover at the same time. It's also extremely important for which kind of lens in this case. If you want to monitor the sky, for example, and see gamma rays, you never know where do they come from. So you need to look as much sky as possible. That is your field of view. Field of view of satellite experiments, especially the one designed for gamma ray burst search, are huge, are like that. Instead, the field of view of Cherenkov experiments of ground base are few degrees, okay? So they really need to know where to point. They cannot just look around and for a search for a gamma ray burst. They need to have an external alert, and they need to repoint as fast as possible. And now, a curiosity. If you're curious about, well, if you want to be able to measure angular distances, you can do that with your hand. Okay, try tonight. How big is the moon as angular side? You know? How big is the moon? Will be more like your finger. So 1.5 degrees, or more like 3 fingers, or you have a feeling? Try tonight, experimental test, okay? I won't tell you how you can remember this. It's very useful. When you want to see distances, when you want to measure angles, you can do it with your hand. If you know the correspondence with the degrees. So I put some extra slides. I won't go to them, but I will leave them online so you can have a look. In this case, I wanted to stress that particle physics, satellite experiments and gamma ray experiments are very are very much similar to particle physics detector of current generation, because we have to observe. We use the same techniques basically. In this case, this is CMS detector, and the different parts of CMS have the same name of what we will find in the Fermi-Lab telescope. Let's go now a bit more into these different satellites methods, but let's start with an historical overview. So the milestones started from, well, the theoreticians that says probably there will be gamma rays from the sky. We expect to have gamma ray emission from non-thermal explosions, for example. Then it took a few years before the first gamma rays were detected from a satellite, Explorer 11. They were appearing as a diffuse emission. It means that the resolution was poor, and also the statistic, 100 photons in total were detected. So it's difficult to clearly point out what is the source. And then in the mid-60s, the first gamma ray source was detected, and it was our sun. Some solar flares were clearly identified, and this gave birth to the gamma ray astronomy point-like sources. Then in the 70s, and even more in the years later, the gamma ray astronomy really have a lot of exciting results. We had a few satellites launched in the 70s that were increasing the number of events, but as you can see here, the angular resolution was quite poor. The pixels were very wide, so you cannot pinpoint the real source. When you compare a pixel in the gamma ray sky of this instrument, for example, with an optical image, we find there thousands of possible candidates. Okay, it's the same that happens now with the the gravitational wave event, when you have a big, huge part of the sky, and it's difficult to understand what is the emitter. That's why we need more powerful instruments with a better resolution. But a nice thing happened in the 70s that, you know, we were in the Cold War, in the middle of that, and the US launched the Vela satellites to control the nuclear explosion on Earth. And what they found were gamma rays coming from the space, okay? And these gamma rays were, so not all bad from nuclear research, was something interesting. The gamma rays were the first gamma ray bursts detected, were really detected by a military mission. Then in the 90s, NASA decided to really invest in gamma ray astronomy and sent a huge mission on a satellite with the two instruments devoted to gamma ray observations, COMTEL and EGRET. Here you have a link, you can click and see the main discoveries of this satellite, if you are curious. But this is just to say that really over the years, more and more interest was gained by gamma ray astronomy, and the sky finally, at the end of 2000, was mapped by EGRET about 180, and you see that it was the first, well, it was a big improvement from the predecessor, but still, it was demanding a more deep, a better resolved studies to understand. You clearly see that the resolution was still poor, quite poor, even for. Then in the late 90s, there were other missions, BACOSAT, SWIFT, that is still on orbit. And now coming to the 21st century, with instruments that are still orbiting, we have Integral, and is a mission, Agile, an Italian mission that was very unlucky because it had to be the predecessor of Fermi, but they had a lot of delays due to problems with the launch, and at the end it was launched only 1 year before Fermi, and the predecessor was a bit, not its best, its best use, because once Fermi was launched, of course, it overcame the other instruments in the Fermi energy band. Okay, so this is the first overview of all the instruments. At the moment, we do not have any emission in the quantum energy range. It's clear, looking at this plot, the impressive technological improvement, especially in the high energy band, so above few tenths of MeV. You see, this is the EGRET sky in 9 years, Agile sky in 9 months, the unlucky Italian mission, and then Fermi sky in 9 months. You see the resolution, how much it improved. Not only the resolution, but even the statistics. You see how many photons you can detect, and then when you have enough photons, you can expect, right? You can do many kind of analysis. Now we can build a detector. We need to go a bit deeply into the interaction of photons. So you are all more or less familiar with this image. This is how a photon in this case is inside a heavy element, but it doesn't change too much if you change element. How a photon can interact with matter. Why do you want to interact with matter? Because you want to detect. In order to detect the photon, you need an interaction that converts your photon into some sort of signal. Okay, and usually what you detect are very often electrons or low energy photons from an electron interaction. So here it's evident that if your photon is at low energies, then you're dominated by the photoelectric effect. This is the total attenuation coefficient. So it's related to the probability that the photon will have this process. So at low energies, you have photoelectric effect. In the middle range, at the MEV range, you have Compton effect. At the higher energies, you are dominated by pair production effect. And this is exactly what happens in the detectors. At low energy, you use photoelectric effect. Then to detect in the medium energy range, you use the Compton effect, and then you are in the pair production regime at high energies, above a few tenths of mega electron volt. I will do a pause in a few minutes, okay? Now, regarding the photoelectric effect, in order to detect photons, you can use either scintillators or solid-state detectors. To understand scintillation, you can imagine how a photomultiplier works. For the photomultiplier, you might have a scintillator that converts an high-energy photon, is converted into an electron that is released by photoelectric effect, and this electron emits low-energy photons. So in this way, since low-energy photons can be collected and registered, you cannot do that with high-energy photons. You need to transfer the energy into low-energy photons that are easily collected, and then these low-energy photons go into the photocathode and become an electronic signal that is multiplied and finally detectable. Instead, you can detect a low-energy photon using the photoelectric effect in a solid-state material, converting it into an electron-hole pair that are registered by the instrument. Okay, as I said before, if you want to detect a source, then you have to get rid of the background. What is the main source of background? Gamma ray detectors. We have seen that gamma ray detectors they need to produce some charged particle that then emit photons, for example, or you use scattering in the material. Then what can be, if you have a satellite, the main source of background in space? Charged particles that arrive. What are the charged particles in space arriving at the detector? Exactly. In general, cosmic rays, right? All the cosmic rays that arrive, they are charged particles that enter a detector, and they are much more numerous than our gamma rays. So we need to get rid of this. Therefore, the first element of a gamma ray detector is a shield that it will not block cosmic rays, because if you block them, then you block also gamma rays and you don't detect them anymore. But simply they recorded them. They see that a charged particle has passed, and therefore you know that the particle passing at that exact moment was a charged particle background. Okay, so this is an anti-coincidence shield. A veto is also called. Then, if you want to build a gamma ray satellite, what do you need? Well, the detector, of course. Either you use Compton effect or scintillation or reproduction. You put your detector inside your shield, but then you still need the two things. What are those? Usually you don't see this kind of stuff flying in the sky, right? What do they have? The satellites. Very good. Solar panels, so that you can get energy from the sun. And then another very extremely important element is that they don't want to keep the data for themselves, right? They need to transfer data. So another element of these satellites are an antenna to transfer data and receiving, of course, orders from Earth. Okay, let's do a small pause.